Okay, here we go. Good morning, everybody. I will be recording today's lecture for the students who are missing today. Okay, so we are looking at Module 6 in chemistry right now, changes of matter and chemical reactions. All right, y'all, this is, I know I said this before, this is one of the fundamental things you've got to get about chemistry, okay? But good news, it's not as difficult as Lewis structures. And y'all feel like you've got the Lewis structures, right? So we're doing good there. You figured that out. Okay. So we're going to actually sort of, I'm not going to say just sort of kind of leave the Lewis structures behind a little bit and now move towards something that's a little more accessible because, I don't know, it's just, it's called balancing equations. We can just balance, just numbers, okay? We'll be working with numbers. All right, so remember this guy. This is Dmitry Mendeleev, and he was the one who had come up with the aha moment about how to place these elements in the order on the way that the table is set up that way, all right? So apparently he had a dream. So in 1863, that's to give you a context, that's during the American Civil War, there were 56 known elements, and they were being discovered yearly. And Mendeleev apparently said he had a dream where he envisioned the complete arrangement of the elements. And here's what he said: I saw in a dream a table where all elements fell into place as required. Awakening, I immediately wrote it down on a piece of paper. Only in one place did a correction need to be made later. So let's watch a little video about this.
By 1869, Mendeleev had been trying to find a pattern to the elements for a decade. Whatever order he and the world's chemists tried to impose, there were still elements that wouldn't fit. A universal theory seemed out of reach. But now Mendeleev hit on a new idea. He made up a pack of cards and wrote an element and its atomic weight on each one. Strange though this might sound, so began the most memorable card game in the history of science. He called it Chemical Solitaire and began laying out the cards just to see where there was a pattern, where they were all fitted together. Now, previously, chemists had grouped the elements in one of two ways, either by their properties, like those that react very strongly with water, or by grouping them by their atomic weight, which is what Berzelius and Cannizzaro had done. Mendeleev's great genius was to combine those two methods together. The odds were stacked against him. Little more than half the elements we now know about had been discovered. So he was playing with an incomplete deck of cards. He stayed up for 3 days and 3 nights without any sleep, just thinking solidly about the problem. Then on the 17th of February, with a snowstorm raging outside, he decided to stay at home. He was exhausted, and he finally dozed off. The story goes he had an extraordinary dream. He saw almost all of the 63 known elements arrayed in a grand table which related them together. It was an incredible breakthrough. I can imagine Mendeleev feeling like so many other scientific pioneers. It's that determination, even desperation to crack a puzzle, and then that eureka moment of revelation. Mendeleev had revealed a deep truth about the nature of our world, that there is a numerical pattern underlying the structure of matter. This is the periodic table as we know it today, and it's rooted in Mendeleev's discovery. It decodes and makes sense of the building blocks of the whole world. Now, although it's so familiar to us, it's on the wall of every chemistry lab in every school in the world, if you really look at it, it's actually awe-inspiring. What's so remarkable is that it reveals the relationships between each and every element in order. Mendeleev had brilliantly combined elements' atomic weights and properties into one universal understanding of all the elements.
Okay, so I think that the orderliness of that is a God thing. God designed it that way, you know, and so whether or not he was, I'm assuming he was using Mendeleev. I don't know if Mendeleev was a believer, but God does speak to us in dreams sometimes, so that could be it. It could be that he was thinking so hard about it that you've done that, right? You're thinking about saying, and then go to sleep and you dream about that thing. And so it could be something like that. But I think this was a God thing to give Mendeleev that information. Now, aren't you grateful that you have that chart to use for every quiz you take, right?
Okay.
Without it, yikes, right? So, okay, so what do we have here? Changes. This is where you're going to start writing in your book. The first thing we're going to be looking at is physical change versus chemical change. All right, this goes all the way back to physical science, if you took that. Physical change is a change in which an atom or molecules in a substance stay the same, even though it's been changed. So I take a piece of paper and I crumble it up. I've just changed it physically, but I can, notice how I have easily reversed, I have easily in quotes. That's because if I tore it to shreds or put it through a shredder, I could put it back together, that piece of paper, right? But it wouldn't be very easy to do that. All right, so typically if we can easily reverse it, then that would usually suggest physical change. Chemical change is a change that affects the types of molecules or atoms in a substance. It fundamentally changes. It is not easily reversed. All right, although you will learn as we go on through the year that all chemical reactions reverse. It's just what speed do they do that. So, but right now think of it this way, not easily reversed. I wouldn't say not reversible, because it can be reversed. But if I take that piece of paper and burn it, how am I going to reverse that reaction? Not easily at all, right? I'm not going to be able to do it. Not in that particular case. All right, so these are some pretty basic definitions for you. You probably remember this from physical science if you took it, and from elementary science. We talked about it a lot, right? Okay. So for instance, if I show you something, oh, here we go. Remember last time when we did our chemical reactions in our little trays, right? And we could see some things happening. So remember the things we had. Maybe there would be a color change. Now the reason it says careful is sometimes color change is due to an indicator changing. For instance, Jiffy Juice, right, will change in the presence of acid. There's no chemical reaction, it just is an indicator. So you have to be careful with that one. But if we have fizzing, that's production of gas. If we have foaming, that's also a production of gas. If we have heat, that's an exothermic reaction. You could also put a slash there, heat or cooling. So we could have endothermic reaction. A production of light or smell or sound. The sound and the odor would also be a gas being produced, popping, things like this. And see, it says change cannot be undone. So we're saying that for this lecture today, once chemical change is done, it's not undone. Okay? It's just later when we do a module and I tell you everyone's reversible, you're going to say, you lied to me. Well, technically, this is true. In physical, we might have color changes. If we put an indicator, it might change colors there. It's not changed. It might just change its size or its shape. It might change its state. For instance, if I have ice and I let it melt, is it still H2O? It is. It just changed state. It went from solid to a liquid. If I boil it and it becomes steam, is it still H2O? Yes, it's still H2O. All right, so nothing there. Dissolving, when I put something into water, dissolve it, it's just moving it around. Bending, crushing, mixing, cutting, that kind of thing is all physical. So for wood, for instance, if I am chopping it up, making it smaller, then that's a physical change. If I'm burning it in the fireplace, then that's a chemical change. Okay, this is a chemical change called combustion. We're going to learn a lot about combustion. Yes?
Can you separate two metals when you melt them together?
I'm going to say, so the question is, can you separate two metals if they've been put together? I'm going to say, in a technical sense, absolutely. And the reason is because they probably have different melting points. You know, you can probably separate them out. It's not going to be easy, you know, so, but I'm thinking you can. All right, so phases of matter. Yay, easy stuff, right? Phases of matter. Here we go. Solid is where the molecules are moving a little. Liquid is where the molecules are moving fluidly. I think maybe these things underlined might be blanks, yes? Mm-hmm. Okay. And then gas is where molecules move at high energy. I think we're going to be using the word heat and energy interchangeably today. It's because heat often is our form of energy that we use. For instance, if we want to change something, we're going by adding energy to it, we're going to heat it up. We're going to put a flame under it. All right, so energy is absorbed as I'm moving to the right from solid to liquid to gas. Energy is released when I'm moving from gas to liquid to solid. So I can reverse those. Those are just change in phase. That's a physical change. And you know from other classes, if I want to, I can evaporate it to a gas. I can take a liquid and evaporate it to a gas. I can take a gas and condense it back to a liquid. All right? Solid to liquid to gas by adding or removing heat. That's exactly what this was saying right here. Solid, liquid, gas. Energy is absorbed. All right, so I'm adding or removing heat to go the other direction. Is that something you're supposed to fill out? I don't know why I put that in there again. All right, so when it changes phase, we call that a phase change, and we call it melting point, boiling point, freezing point, and then the word condensing. So you can see in each one of these cases here, if I have a gas, it can either be condensed back into a liquid. It says here, there's this word we're going to look at in a minute called sublimation. And that is a special condition where a solid and a gas can go right between each other, skipping the liquid phase, just skipping the liquid phase under certain conditions, okay? And then liquid, of course, we can freeze it, we can vaporize it, all these things. All right, so those are just phase changes. There's a word over here on the right called enthalpy of a system. We'll get to that in a future module. We'll get to entropy and enthalpy and yikes, okay. All right, now the kinetic theory of matter. Kinetic means moving around, okay? The opposite of kinetic energy would be potential energy. So if something's moving, it possesses kinetic energy. So molecules and atoms are in constant motion. Why are they in constant motion? Even in a solid, even something that's frozen, why is it in constant motion?
Energy?
Okay, but what about it is moving?
The nucleus?
Almost. What's spinning around the nucleus?
Oh, the electrons.
The electrons are always moving. They're always moving. So by virtue of that, whether they're a solid, a liquid, or a gas, those moving electrons are always moving. In this table, if we could get closer down and see in there, we would see those electrons spinning around there. So they're constant motion. Now, the higher the temperature, the greater their speed will be. That's because raising the temperature would be adding energy. So remember I said heat and energy are going to be interchangeable here when we add heat to it. So here you can see I have my solid. If I add energy, it'll melt it, become liquid. I add energy, it'll become gas, and then vice versa. I can remove energy from it. So the question here, why do gas companies store their gas in liquid form? Do y'all have propane at your place? Have a big propane tank? Yeah, I've got one of those too. And when those guys come out in the big trucks to fill it back up, you know, they have a hose that goes over to it, and it says LP on it, liquid propane. And in your house, is it still liquid? It turns into the gas, right? And the reason it turns into the gas is because you let it loose. You let it loose because it's under that pressure of that tank. It has to be in that very, very pressurized tank. Same with that guy's truck. Because I think the boiling point, because I asked him one time, that it was in liquid form, but as he's putting it in, I could see the gas coming out, and smelling and stuff. And I said, so that's, that must have a really low boiling point. I think he told me it was like negative 40 or something for it to boil, So in other words, to turn into a gas. So it has a very low boiling point. So when cooling a gas to a liquid, it reduces its volume. We're going to learn this when we learn about the gas laws with a guy named Charles Boyle, Boyle's laws. So when you cool it, when you get it colder, this makes sense, doesn't it? It's going to take energy away and put those moving molecules closer together. Okay, so I get closer together, my volume gets smaller. If a substance is heated 10 degrees, will the molecules move faster? Of course. Yeah, when heated at all, they'll start to move farther apart. All right, so as soon as you let that gas loose, it'll turn into that gas phase, and of course it's flammable. We put a little spark on there, and we cook our food. So that's why they put it in that, keep it in liquid form, because it doesn't take as much space. It's easier to transport that, all right, to bring it to my house. Bring it in the gas form, you'd have to have a big old Zeppelin coming out to my house or something like that. All right, the kinetic theory of an atom's movement. Molecules and atoms are in constant motion. The higher the temperature, the higher their speed. We already had this one on there, right? I just have those underlined now. So here they are, moving around. So moving, definitely still moving on the solid. moving more in the liquid, moving the most on the gas. With kinetics in mind, to change phase, you can add or remove heat. Remember, I'm using that word heat as energy, all right? In order to move the gas phase from the liquid phase, you must increase heat. I believe that's something you're supposed to fill in. In order to move from the solid phase to the liquid phase, you must increase heat. In order to move from the gas phase to the liquid phase, heat must decrease. You got to cool it. And then in order to move from the liquid phase to the solid phase, heat must decrease as well. So it's kind of interesting. I remember this from a college physics course that a professor told me that if I were able to take a cup of water and put it under immense pressure, I would freeze it. It wouldn't have to be cold. I could just, the pressure alone would do that. All right, so this pressure thing is part of that. So we pressurize that propane, it turns it liquid. Theoretically, if I kept pressurizing that, I could turn it solid. Okay, so here we're looking at, we're going to talk about water specifically in a minute, but right here I just wanted to show you our water on the bottom, H2O, all compacted together in its solid form as ice, then as liquid water in the middle here, and then as gas at the top right there. They're all still H2O, they're just in their different phase right there. All right, and now we're going to talk about when we compact things like this, we're going to look at something called density. All right, in the old days, before they rewrote your book, density was covered in Module 2. So that's how basic it is, y'all. So you kind of get a little bit of a breather on this module, if you ask me, because the concepts are fairly simple. The most difficult thing is just learning to balance equations, which is a breeze, okay? All right, so density, here's the definition we'll be working with, the amount of mass in a given space, or how tightly packed it is, okay? The amount of mass in a given space. Very simple. I heard somebody comparing it to if you pack your suitcase. So I don't know if you've ever gone on a long trip or something and you pack your suitcase and you pack it so full you have to sit on it to zip it up and this kind of thing. Well, that is a densely packed suitcase. The suitcase is the same shape as it was before, but I could also take, have you ever heard people that take an empty suitcase with them so they can bring back souvenirs? So if it's empty, when they're taking it, it's going to be really, lightweight, right? It's going to be very loosely packed. Okay, so loose, not dense, not very dense. All right, so look at this space. I've got a cube on the left that has low density, and I have a cube on the right. Let's say we had a cube of styrofoam versus a cube of lead that were exactly the same size. Do you see how the lead is always going to be heavier that way? Yeah. All right, so that's because lead happens to have molecules, have atoms, because it's an element, that are packed really closely together. All right, they're packed very closely together. Styrofoam is packed very loosely. That's one of the things that makes it, it floats, it's a good insulator, this kind of thing. There's a lot of air in it. You could squish it, I guess. All right, there is a little bit of math on this one. We're going to be looking at this density formula. And this is the main one right here. Rho, you can draw it as a little lowercase p, but it's a Greek lowercase letter, rho, equals mass over volume. So is that written for you? You're going to write it several times in some boxes, right? So this is the main one. Density equals mass over volume. And our units are going to be right down here, either grams per milliliter or grams per cubic centimeter. Remember, milliliter and cubic centimeter are the same thing. And cubic centimeter is the same thing as saying a cc, like in a syringe. 3 cc's is equal to 3 milliliters. And that's going to be a grams per milliliter, grams per cc. And then we're going to take this formula and we're going to move it around a little bit, do a little algebra. Just so if you memorize it this way, if you just memorize this one, you're cool, you're good, all right? But if we memorize all the different applications of it, then you don't have to think as much, okay? So here we go. This is the main one, P equals M over M over V. I was thinking of F equals MA. V equals M over P, and M equals P times V. Okay, remember P is rho, I should say rho, mass and volume. So we're looking at rho, density, mass, and volume. And there's our grams per milliliter, or grams per cubic centimeter. cc. Okay, so those are the 1, 2, 3, you had 3 boxes, yes? Mm-hmm. To put the 3 different forms in there. So then if I ask you a question on density, then your question is going to be, what are you asking for? Are you asking me for the density, which would be this first formula here? Are you asking me for the volume, or are you asking me for the mass? And then I can use whichever one of those. And look how easy those formulae are, right? Pretty easy breezy. Yeah, no weird stuff there. Also, you can think about this, right? You've done a density deal similar to this in other classes, I assume. I think we're supposed to do something next week with density. It always drives me crazy because I have to use oil, you know, and I can't dump oil down the sink, so I always have to get rid of it some way. So I don't like density experiments, but they're kind of fun when you see. If we had this many, it'd be pretty cool. We won't have that many, guaranteed. All right, we're gonna do an example here. A gold miner has found a nugget of gold, and somehow he knows its volume already. The volume is 0.125 liters, so he knows the volume. Magic. So he's trying to figure out the mass. To me, it would be easier if he would know the mass, wouldn't he? Because he could weigh it. He's trying to figure out the mass of gold. All right, here's our three choices. If he's trying to find the mass, so which one of those formula are we going to use? This third one down here, m equals rho times volume, yes? Because we already know the density. All right, so the density of gold is 19.3. By the way, not on your chart, but on my chart, my periodic chart of the elements, density's on there. It's written right on there, okay? So for y'all, I'll have to give that to you. It'll be given. But there are some, like my periodic chart of the elements has two sides. So I have a bunch of information on the front side and a bunch of information on the back side, including density. Okay, so here we go. It's going to be m equals 19.3 grams per milliliter, that's given to us right above, times 0.125 liters. There's a problem with our equation. What's our problem? Maribella knows what it is.
Later should be milliliters.
Our units don't match. Our units are not matching here. And so we're just going to switch it over. Now, going from liters to milliliters is going to be pretty easy. How do we do it? Well, we can go through the factor label method, and I'm going to do that for you so you remember what we're doing. Or we could just move a dot over, the decimal point over, right? Okay, so volume from liter to milliliter, here it is, 0.15 liter, that's given to me, over 1, remember I put that over 1, and then multiply by the conversion relationship, that's 1 over 0.001 liters, brings us to 125 milliliters. Do you see how I just moved that? Yeah, that decimal point over 3. 3 zeros, moved it over. Okay, and that's fine with me if you do it that way. All right, now it's easy, right? We're going to take our m equals 19.3 g over ml times 125 ml, right? There it is, and there's our answer, 2,412.5 grams. All right, we were looking for mass, and our answer came out in grams, our milliliters canceled, so hooray, that's good. Okay, now, if you want to be official on significant figures, which personally I'm not that big of a stickler for that, the official answer would actually be 2.41 times 10 to the 3 grams. I will accept 2,412.5 grams. Okay? All right, so at $60 a gram, the nugget that he found was worth $144,600. Wow, nice. It's time to go mining for gold, right? Yeah, I found a gold coin in my mom's stuff. I was going through my mom's stuff and I found a gold coin and I looked it up and it was worth $19,000. And I said, wow, it was this big, little tiny thing. Like, it was 1 ounce. Yeah, and I was like, cool. Gold is pretty dense, so even a small amount of gold actually weighs quite a bit. It's pretty dense. All right, now, there are other density problems, and they're in your thing right there. We're going to skip through those. Y'all do those at home, please, okay? And we're going to, they're not that difficult. You just go do the math right there. So we're now going to 6B, Lab 12. When I do want to take up your books at some point. Can't figure out when to take them up that you don't need them, right? So like you're going to need them to study next week, for next week. Yeah, maybe, yeah. I just want to take them up so I can record your test grades and I can give you a lab grade. So I can give you a first quarter, if you will, overall grade. Right now your grade on Jupyter Grades is only based on your quizzes, which is not a reflection of your grade right now. Okay, so don't get discouraged by that. But I need to enter that information in. Okay, so I'm gonna have to take those up here. And when I do, I want to see those boxes that had all those other on your own problems filled in. Okay, Yeah. Now, if you find a blank page, you know, that's not going to reflect well on your grade. Have stuff on your written there. Okay. All right, we're going to talk about water. Remember, it's polar. Here's our polar bear. All right, so remember what that means. It has those partial charges on it. So what about it? What's the big deal about water molecules? Well, it turns out that hydrogen bonding keeps the water molecules closer together as a liquid than as a solid. So since we have those, I'm going to go back for a second. Since we have these bonds formed between the positive H and the negative O, all right, we form these little bonds called hydrogen bonds. Okay, and when they get, when it turns solid, they actually kind of stiffen up, almost like they freeze and they stiffen up like this. And it actually makes the solid version of water bigger, all right? So it gets larger. And because of that, it's less dense when it floats because they move the molecules apart. Does that make sense? They're moving the molecules a little farther apart. This is, no other substance does that. Typically, if it's another substance, let's say for instance alcohol, rubbing alcohol, when you get it cold, it gets closer together. Most things do. Water's the one thing that doesn't. And you probably have realized this. If like for instance, I have to use cold alcohol for some of my biological procedures when we get DNA out and stuff like this, and I put it in the freezer and it doesn't freeze. Yeah, it doesn't freeze. When water freezes, that's because everything gets nice and close together, energy's lower, this kind of thing. You can eventually freeze it. Otherwise, lakes would freeze from the bottom up, killing fish. Here, there, so I wanted to show you the hydrogen bond right there. They kind of stiffen up. Remember, there's a covalent bond between the hydrogen and the oxygen, and a hydrogen bond otherwise. So if you put a water bottle in the freezer, it breaks the water bottle. Even plastic water bottles can crack. But don't put a glass bottle, like a glass bottle of Topo Chico. Don't put that in the freezer. It's going to break. That's how powerful that movement is. Also, this is showing our little fish surviving because the ice freezes from the top down instead of from the bottom up. If it froze from the bottom up, then we would have dead aquatic animals. And you think, well, big deal. Well, actually, they're part of the food chain. We need those guys to help us survive. Okay, so these are the things I think you're supposed to write down. What makes a water molecule unique? It's polar. It's the universal solvent. It exhibits surface tension. You can float a paperclip on there, right? It's less dense as a solid. We're going to actually see a video that tells us about each one of these. Adhesion, there's something called cohesion, and there's something called adhesion. Cohesion, it sticks to itself. Adhesion, it sticks to other things. It exists on Earth naturally in all three states. It's the only place we know in our universe so far where we have all three states of water in all three forms. They say they found some water on the moon under the surface. Not sure how they found that, but it's frozen. There's no liquid water there. It has a high specific heat. That means it takes a lot of energy to boil it. It's one of the highest boiling points of anything that we know. It's 100 degrees C. And of course it exhibits hydrogen bonding, which gives it those unique characteristics. And so if you write each one of those down, and when we watch the video, you might want to just make a little note next to each one to help you remember what it means. If you don't want to, that's okay. That's up to you. All right, here comes our video. So go through each one of those as far as I know.
Life, as we know it, would not exist without water. Over 70% of the planet is covered in water, and our bodies are around 70% water. But why is water so important? The structure of a water molecule and the fact that it is capable of forming hydrogen bonds with multiple other water molecules simultaneously provides water molecules with some very unique characteristics. These include the ability to act as a universal solvent, the properties of cohesion and adhesion, a high surface tension, a high heat capacity, and changes in density based on temperature. Let's take a look at each of these in turn. Water is often called the universal solvent, which means that many substances dissolve in it. Water's solvency has to do with the polarity and hydrogen bonding ability of water molecules. When a salt, such as sodium chloride, is placed in water, the negative ends of the water molecules are attracted to the positively charged sodium ions, and the positive ends of the water molecules are attracted to the negatively charged chloride ions. This attraction causes the sodium and chloride ions to break up or dissociate in water. Why is this important? Since our cells are mostly water, these solutions of ions and molecules allow chemical reactions to occur much more frequently, which is an important feature to allow organisms to respond to their environment. Water molecules are also cohesive and adhesive. The hydrogen bonds in water cause water molecules to stick together, a property known as cohesion. Polar bonds also give molecules an adhesive property, or the ability to cling to other polar surfaces. Why is this important? Well, water fills the internal transport systems of plants and animals. Because of these cohesive and adhesive properties, water allows for the efficient transport of nutrients and waste within an organism. Water also has a high level of surface tension. Because water molecules at the surface are more strongly attracted to each other than to the air above, water molecules cling tightly to each other. The surface tension of water explains why it beads up on waxy surfaces and why water-striding insects are able to walk on the surface of water. Water has a high capacity for heat. What this means is that the many hydrogen bonds that link water molecules let water absorb a large amount of heat without changing its chemical state, for example, from liquid to gas. This not only stabilizes the temperature of bodies of water, such as lakes and oceans, but also plays an important role in the physiology of an organism. Since life is based on water, and the temperature of water rises and falls slowly, living organisms are better able to maintain their normal internal temperatures and are protected from rapid temperature changes. And finally, the density of water is based on its temperature. However, unlike many other compounds which contract when they freeze, the configuration of the hydrogen bonds in water causes it to expand when it freezes. This expansion causes ice to have a lower density than liquid water, and therefore ice floats on liquid water. If ice were more dense than water, it would sink, and ponds and lakes would freeze solid, making life there impossible. Instead, bodies of water always freeze from the top down. The ice on the surface acts as an insulator to protect the water below from freezing. This protects aquatic organisms so that they can survive the winter.
All right, there we go. Real quick, that word I said earlier, we're going to talk about sublimation, is where they can skip a step. And you can take a solid and it sublimes over to gas. It goes straight from solid to gas. It skips the liquid phase. So that happens now and then, and it's got that special name. If it goes the other way, which I can't even think of an example of that, we call that deposition. All right. Now, homonuclear diatomics, we've already talked about these in a previous module, but in the old days it brought it up here, and it's going to be important for our next step that we're going to take. So we're going to remember our homonuclear diatomics. Remember what that means? They always go around with a twin, right? They're always going around together. They're made up of two atoms that are the same. Our organic molecules, hydrogen, oxygen, nitrogen, and then column 7, fluorine, chlorine, bromine, iodine, and acetine. All right, so we have hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. Do we have bromine over here? Yeah, okay. Are they all there? So here is a mnemonic, and if y'all, I don't want to get in trouble with anybody, but this mnemonic is useful to help you remember what they are. Have no fear of ice cold beer. Sorry, but beer rhymes with fear, so we could have said, have no fear of ice cold. Near beer. Yeah, I don't know. Beer. Yeah. Cheer. Yeah, but we need to be. Yeah. So this, if you remember that, you remember hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. Yeah. So anyway. I thought it was kind of easy that way. All right, so what we're moving, now that we remember those, okay, we're going to remember when we see them in a chemical equation. So now we're going to be looking at chemical equations, okay? So here we go, balancing chemical equations. You can determine if a chemical equation is balanced by counting the atoms or molecules of the product and reactant. The idea here is whatever we start with, and it goes through a chemical reaction, we have to have the same number on both sides of each of those items, okay? We can't lose anything. That defies, in fact, remember the law of conservation of mass. All right, whatever I start with, I have to finish with. See, I had 67.25 grams here at the beginning of whatever I was reacting, and whatever I made over here, I have the same amount. We did that experiment. Remember, we dumped this stuff in, and it changed the Jiffy Juice, and we had to weigh it before and after, and it was exactly the same, right? So remember that law of conservation of mass requires that we have a balanced chemical equation. So a chemical equation says this. We have products. That's the stuff we're making. Production, okay? We're making something. That's going to be on our right side of our chemical equation. The reactants are on the left side of our equation. That's going to be the stuff we're using to make the products. They're reacting together to form a product. And then the balanced chemical equation means that we're going to make sure that the same number of atoms are on either side, each side, the reactant side and the product side. Okay? Does that sound easy enough? Okay? All right. So here, it's all about balance. So most of the time, y'all, and we're going to do several of these practice today, and y'all are going to work them yourselves, okay? Most of the time, we're going to find these pretty easily. There are some times that there are some that are more challenging. All right, and just one thing you need to remember is that there's no fractions in chemical equations, okay? No fractions, no decimal points in chemical equations themselves. So consider this. We're going to take, now look at my H, it's got 2, right? Because we know it's a homonuclear diatomic, right? We've got 2 of those on this side. How many hydrogens do, oh wait, we have 2 here plus 2 here. Not plus, multiplied. So how many hydrogens do we have on this side? We have 4. 2 times 2 is 4. How many do we have on this side? 2 times 2 is 4. How many oxygens do we have? 2. See this big 2 on the product side? That also goes for the oxygen. So how many oxygens do I have on the product side? 2. Do you see that? Okay. So this is a balanced equation right here. All right? Notice my reactants are on the left, my products are on the right, and a chemical change has taken place. In fact, we're going to see in a second, H2 and O2, when they're by themselves, as their homonuclear diatomic, they're almost always a gas. All right, so I put these 2 gases together, and I'm going to crash out possibly a liquid in my products, right? Liquid water right there. Pretty cool. All right, so this is important right here. So take a look at this. So here's that same equation that I just told you about. I've told you it's balanced. And the big numbers at the front, those are 2's, and our little numbers here. Look at these little numbers. See this? There's a 2, and a 2, and a 2. Those are called our subscripts. Okay, and what I need you to know about the subscripts, don't mess with them. You cannot, you understand? You cannot change those. You can't do it. Don't do it. It's like, what do you call that? The cardinal rule of chemistry. Don't mess with the subscripts. There's going to come a time when you're going to have to figure the subscript out. Like, for instance, if we end up on the right side, we have a product that's hydrogen, you're going to have to remember, oh, hydrogen never goes around by itself. It's always going to be an H2. So you'll put that 2 down there because you had to remember it was a homonuclear diatomic. That I'm not talking about. But right now, in order to balance this, I cannot balance it by changing the subscripts, okay? Don't touch them. If I catch you doing that, I'm going to have to kick you out of chemistry. Oh, now you're going to do it on purpose. Don't do it. Don't do it. So these guys right here, check them out. These are called the coefficients. That is what you change, okay? You can change those all day long. All day long. But they have to be whole numbers, and they have to be positive. Can't be negative, can't be fractions. Okay, so that's nice. I don't know about y'all, I don't care for fractions. I don't like them. I also don't like negative numbers. I can't count backward. In history class, in the negatives and in the BCs, I'm all messed up. I can't figure out how many years went by. I just can't do negatives. My brain's not made that way. So, don't mess with the subscripts. Do rearrange the coefficients. All right, so we need those words. Coefficient, subscript, we know those. All right, so let's look at this one. We have CH2O. We're going to add some oxygen to it. This is a combustion reaction. When I start with a fuel and I put it in the presence of oxygen, then I spark it, we're going to burn. And we're always going to make H2O and CO2. Now, y'all, we're going to try to figure out if this is balanced. Okay, so let's look. Here's the hint I have for you. The first hint is, let's start with the atom there's only one of them on each side. So that's carbon. See, there's an O here and an O there. That gets a little complicated. So let's start with our carbon in our organic matter over there. How many carbons do we have on the left side in our reactant side? One. And look over here in our product side, how many carbons do we have? Just one. Yeah. So the carbons are balanced. Awesome. Okay. So now let's move on to our hydrogens and our oxygens. Now hydrogens only here, so we have how many? 2. And how many over here? 2. All right, now we have to deal with our oxygen. We have 2 oxygens here. And this is kind of nice over by the carbon dioxide. See our 2 oxygens there? But don't forget we got an oxygen there, but once again we have an oxygen there. All right, so are we balanced in this equation? Yeah, we're balanced. Nice. Okay, that's very nice. I didn't have to put any coefficients in. It's already balanced. That's excellent. Now let's check this one out. You can probably guess this one's probably not going to be. Let's start with our carbon. We have 1 on our reactant side. That's the left side. We have 1 on our product side. We're good, right, on our carbon. Now let's look at our hydrogen. We have 4 on our reactant side. How many do we have on our product side?
2.
Only 2. So right away, if I ask you this question, is this chemical reaction balanced? Your answer would be no. Don't you like those? I haven't asked you to balance it. I just asked you, is it balanced? And you can just say no, it's not balanced. Okay? Now, next thing I want to tell you about, see that little thing with the G right there? That's that right there. This little G next to each one of this is telling us something about these molecules right here. They're gaseous form. They're in gas form. That's what G stands for, gas form. So I have methane gas, and I'm going to burn it with oxygen gas, and I'm going to end up with CO2 and H2O, which is what you get when you do a combustion reaction, every time if you're using carbon. Okay, but since it's not balanced, let's go ahead and see if we can balance it. We can balance that H4 on our reactant side by doing what to our H2 on our product side? What can I do? I can't put a 2, I can't mess with the little 2, right? But can I put a 2 in front of the H2O? Yeah, that'll do that. So that'll give me 4 hydrogens. Now let's look at our oxygen. I have 2 here, I have 2 here, yikes, I got 1 more over there. So how can I fix that?
Put a 2 on both sides?
Yeah, we can put a 2 over there, but then we're going to have too many oxygens, right? All right, let's see how we do it. Oops. And that fixed it. So we see our 2 over here in front of our O2. That fixed it by not messing up this because our O2 was there, and our O2, this 2 in our H2O goes for 2 in the front, goes for the H's and the O's. So do you see how I have 2 oxygens in the H2O and 2 oxygens in the CO2? That's 4. 2 times 2 over here, I have 4. Now, there's a reason why this balancing must take place, all right? Because we are going to be looking at the fact that we can't really end up with leftovers. Now, when I say this to you, in the chemical reaction, there needs to be no leftovers. If we end up mixing things together and we don't use all of one of the things we're mixing, that can be left over. That's called a limiting reactant. We're going to get to that. So but just right now, make sure we need to have everything covered. Here's why. If I'm going to take CO2 to make CO2, all right, I want to take carbon and oxygen, and I want to make CO2. We're going to see how in this little short video right here. We're going to take that. Where's our oxygen coming in? Oh, there's our carbon and our 2 oxygens right there, okay? So that's nice. We started with 1 carbon and 2 oxygens, and we used them both to make carbon dioxide. So that's nice and balanced. I have my lovely little carbon dioxide molecule right there. Very cool. We're going to see, though, in this particular case, how we don't want to have anything left over. A chemical reaction must start with its reactants and end up with its products and have no extra atoms left over. No extra atoms left over. So we know what this one is. This is one we just did, right? Okay, so let's say we didn't put our coefficients in front of it. So we have a CH4 and an O2. CH4 and an O2. Okay, we're supposed to get CO2 and H2O, but let's see what happens when we do this. All right, so I'm going to react them together. My oxygens are going to come off there, my hydrogen's there. And now I have my CO2, but what do I have over here? What are those yellow things? Those are leftover H's over there. They're just hanging around over there. What are they supposed to do? Okay, they don't have any place to go, and that's a problem. All right, so they must balance. We'll see it in a second. Balanced by changing the number to the left, which is called the coefficient. They can be changed in any way as long as they're whole and positive. You cannot change the subscript numbers, you know that. An unbalanced chemical equation will result in the following cases. Not all the products will be made. There will be leftover atoms, and we cannot do that. So often the symbols showing the phases for the substance are shown. S is for solid, G is for gas, L is for liquid, AQ is for aqueous, meaning it's suspended in water. It's a little different there. Those are not important right this minute. They will be important later in some of our, just remember when you see those little things on there, sometimes they make it very crowded and messy, but we'll need them at one point. There's at least one module we're going to need those. Okay, so here it is. We know that we balance this by putting a 2 here and putting a 2 there. And now we're going to see how it fixes everything. All right, we're going to react them. There they go. And check it out. We got our CO2 and our 2 H2Os. Yay. Okay, everybody's happy now. Chemistry is done. There we go. All right, we're going to have an example where this question here is going to ask you, is this chemical reaction balanced? So take a look at it and tell me right now, is it balanced? Anybody got it?
I think it is.
Okay, I'm gonna
Actually,
point
no, I don't
you.
think it is.
I'm gonna ask you to take a look at this right here.
Yeah, I was just thinking
What's the problem with calcium?
that there's 2 on the right and there's only 1.
Yeah. There's only 1 in the reactant side and there's 2 on the product side. So this is not a balanced equation. And that is the question. So if I ask you the question, is this balanced, you're going to say no. So when I give you an equation that has coefficients already in it, you might be tempted to say, well, the coefficients are already there. It must be balanced. Oh, look at it more closely than that, okay? Because this is a trick for you. Now, this is a video, but this is the guide that goes on and on, you know. So we're going to skip that. All right, we're going to skip the video portion of it because y'all got it. Y'all got it that it was not balanced. Okay, so that's example 6.2. I don't know if you're supposed to write it down. But if you have several like that in your book, in your practice problems, as well as remember you have a study guide and practice problems. You remember that, right? Do those practice problems. I'm going to take y'all to practice these balancing problems. All right, here's the next one that's also going to say, is this one balanced? This, you should recognize this chemical equation. What is that chemical equation? Photosynthesis. Bingo, that's right. Is it balanced? You should be able to say yes right away because you know it's photosynthesis, and that's the way we write it every single time. 6 CO2 plus 6 H2O gives me C6H12O6, which is glucose, plus 6 O2. So yes, this one is balanced. All right, so if I ask you this question, your answer would be yes. All right, I will tell you that on your quiz next week, if I do ask you, is this balanced, it might be one question because it's just too easy, right? I'm going to actually make you balance some equations. Okay, so let's go do that now. Here is our equation, P4O10, I don't even know what that is, plus H2O will give me H3PO4. Now, first thing we're going to see is everything on the left, on the right. Yes, we have hydrogens, we have phosphorus, we have oxygens. Okay, so let's look at P on this side. Before, it only has 4. See how I've made my little table down here? In our reactant side, I have 4. In our product side, I only have 1. So right off the bat, we know it's not balanced, but let's go ahead and take account of everything. Next, our oxygens, what do I have? I have 10 right here, but I also have 1 in my H2O. Do you see it? So 10 plus 1 equals 11. I will tell you this, anytime you see an odd number, it's gonna drive you crazy a little bit, okay? Because odd numbers will end up sometimes with fractions, and not in this case, but sometimes with fractions. And just remember, if you end up with a fraction, you have to take the fraction out. In other words, you have to multiply the whole thing by the upside down fraction. You know what I'm talking about? That'll happen sometimes, okay? With that, what is that called? The reciprocal. So you never, ever, ever leave a fraction in a balanced equation, okay? Don't ever do it. Those are the hard ones, though. And then our hydrogens, we have 2 right here. And we have 3 on this side, right there. So can anybody think what we could do to make this better? I'm trying to think where we should start. Let's start with the phosphorus. So that'd be easy. What can we do to get phosphorus to even?
You have to multiply the whole thing by 4.
Say that again.
Once you have to multiply the whole thing by 4.
Well, don't be multiplying the whole thing yet. Let's just put our coefficients in. Okay, we're gonna only multiply the whole thing if we have a fraction. Right now we're not dealing with that, okay? So what are we gonna do? What are we gonna do here on our product side?
Put a subscript after.
No subscripts. Can't mess with subscripts. Don't touch the subscripts. Don't touch the subscripts.
Wait, I mean the coefficient.
Okay, thank you. She meant to say coefficient. We're going to put a coefficient in front of it, and that coefficient is going to be 4. Do you get it? Okay, so that 4 is going to apply to everything now. All right, so I'm going to end up with 4p. Yay, that's good. But I also totally messed everything else up. But that's okay. We can go fix them on the other side now. So now that I fix this by putting a 4 there, how can I fix these other two things? I think 4 times, here we go, 4 times 4 is what? 16. And how many do I have over here?
11 or 10.
Well, I actually do have 11. 10 plus 1, all right. So can I fix that?
Yeah.
I can do something. We're not going to have to mess with this. I can do something right here. I can put a coefficient right in front of there. And how can I do that? I hope I didn't say that wrong.
3. Wait.
Then look at our h's as well.
Put a 6.
So if there's a 4 here, I have a 4 in my 3.
Do 6. Yeah, it'd be 6.
Right over here?
Mm-hmm.
Okay. So, anybody lost? Okay, a little bit? Okay. The next thing's going to show us how we're going to keep account of everything. Okay? So, the easy part was putting our 4 there, which what's it going to do to my p? It's going to tell me I'm going to have 1 times 4, so my 4, that's right there. Now, putting the 6 there, look what happened. I had 10 plus 1 times 6 now is going to give me 16. I had 4 times, what am I doing? 16 for my O's, 10 here, then my 6 there, okay? And then my O's, 4 times 4 is 16 there. Do you see? Hooray! And then my hydrogens, I had 2 on this side. Oh, I didn't finish that. Okay, so I put 2 times 6. 2 times 6 equals 12. I should have had a little times 6 right here. Do you see why? Next to my 2 on the bottom there, I should have times 6 because the 6 is that coefficient. Does that make sense? Sorry, I left that off. All right, but do you see how I'm keeping account of everything? Was this one a little more challenging? A little bit. Okay. If you get those numbers fixing in there, I would say if it's not coming to you like that and you can see that 6, some of you can see that 6 right over there, then go ahead and make your little chart. And then it'll come out like that. Because I'm looking at 11 saying, I'm done, I'm out. I can't do 11. Okay, but it's okay. It's all right. Okay, so we're going to do this one now. This is in your book. You have number 7, 8, 9, whatever in your book right there. This is number 7. So we have HCl in its aqueous form, plus calcium in its solid form. We're going to get calcium chloride, aqueous, plus H2. First thing, are we balanced? You can tell right off the bat we are not balanced, right? Because I have 2 calciums on my products, I have 2 hydrogens on my products, and only 1 on my reactants. So, is this going to be an easy fix? I like the fact that we're working with 2s. That's nice. Okay, so what should we do? So y'all go ahead and write down how many hydrogens you have on each side. 1 and 2. Chlorines, 1 and 2. Calcium, 1 and 1. Calcium's all right. All right, so if we don't have to mess with calciums, we might have to still, but I don't think we have to in this particular case. So what can we do?
You can put a 2 in front of the HCl.
Right here at the front, and that'll take care of my chlorine. Will that take care of everything?
I think so.
That looks like it takes care of everything. Let's see. Nice. You get that? That's all we had to do. Yes.
How come there's a gram and right there and then a solid right there and then AQ?
Again, G is for gas. It's not gram.
Oh.
It should, because it's in the little parentheses like that. It's just showing you what state it's in.
Okay.
And I feel like it's a, well, so I need you to know what they mean. There's going to come a module in the future you're going to need them, okay? Right now you don't. They're in your book that way just to get you used to seeing them, okay? Right now it wasn't important that they're gas. We don't care right now. We will eventually, okay? So, but yeah, it looks like gram, but no, since it's in the parentheses, you know it's gas. And I believe it's also another subscript, if I'm not mistaken. And maybe I didn't do that quite right. I thought it was a subscript. Okay, here's our next one. Ready? HBr in its aqueous form plus sodium in its solid form is going to be sodium bromide in a solid form. And H2, bummer, we were almost there, right? We were almost there. What do we have to do? That hydrogen messed us up, right? So what do we have to do? There's only one thing we can do at the beginning, is we can put a 2 in the front, yes? Over by our HBr, but what does it do to our Br? it gives me 2 of those now. So now I have to go fix that. I put a 2 here, but what does that mess up? My sodium. But is it that bad? Not really. What can I do to that sodium? I can give 2s, just hand 2s out like they're free. Here's a 2 for you, and a 2 for you, and a 2 for you. Okay, do you see it's balanced now? Yeah, now that's it actually can be kind of fun on these easier ones. Some of the more difficult ones are more difficult. I believe this one is number 8 in your book, that second one there. All right, are we good? All right, let's do the top one here. Silver chloride plus zinc. So silver chloride's aqueous, zinc is solid. We're going to end up with zinc chloride and some leftover silver. So silver can be by itself. It's not a homonuclear diatomic, so it's okay that it's by itself. Over there, it kind of crashes out as a solid. In fact, if I have silver chloride and some zinc, if I want to get silver so I can make jewelry out of it, this is a way to get it from that rock of silver chloride. First of all, are we balanced? No. Is it going to be an easy balance? Yeah. I like 2s. I love 2s. So that 2, I can put a 2 in the front, yes? That'll take care of my chloride, but it'll mess up my silver. But is my zinc going to be okay? I think zinc's okay. There it is. So 2 at the front and 2 at the back. And everything else is balanced. Get it? Mm-hmm. Not too bad. As long as we work on 2s. Wait till we have some 3s in there. Oops, and my next one, it's magnesium chloride. I'm sorry, that 2 is big. It should be a subscript down there, that 2 right there. It almost looks like a C12, doesn't it? That should be a small 2. So magnesium chloride plus, what is that? H2S, which is aqueous, that is sulfide or something like that. Is going to give me magnesium sulfide and hydrochloric. Now, is it balanced? If you've got a subscript in the front and no numbers in the back, it's not balanced, is it? So our hydrogen's the problem. So what can we do?
I think you just have to put a 2 by the.
Oh, because our chlorine needs to be balanced too. Because I'm forgetting about that too, because it's not down where it needs to be. Mm-hmm. So I think we can just fix it by putting the 2 right in front of the HCl. Does that work? Mm-hmm. That takes care of our chlorine and our hydrogen. Hooray! All right, are y'all catching on? You getting it? Not too bad. If you like puzzles, you might like doing balancing equations. And if you want more challenges, fear not, there will be more. In fact, okay, so we've done 7, 8, 9, and 10. I'm guessing 11, 12, and 13 might be more challenging. Okay, are we good on this one? Everybody good? Okay. Also, keep in mind, since I'm recording this lecture, if you want it and you want to listen to it again, if you want to torture yourself, I can send it to you. Let's try some tougher ones. Here we go. We have, whenever you see, y'all, we're looking at a combustion. Oh my goodness, look at this. Look at this. C18H32O16. What? Those are a lot of really crazy numbers right there. Okay, so right off the bat, we are not balanced, are we? Okay, this might be a good choice to go in and make your little chart. How many carbons do I have on this side? 1. How many do I have on the product side? 18. So already you can tell me, I can put an 18 in front of CO2, but that's going to be 18 times 2 for my oxygen. Wait a minute, 18 times 2 for my oxygen plus another oxygen right there. I've got 16, 17, 18 over there. That was so close, so close. This is when you say, why do you have to be a homonuclear diatomic oxygen? It would be so easy if you were by yourself. Okay, so you want to start with that 18 at the front? Is that a good place to start? Let me check my notes. Yes, that is definitely what we want to do. We want to start with our 18 in front of CO2. That's going to mess everything up on the left side. So we need to do something with our H2O. What do we want to put over there? Because we have 32 hydrogens. We have 2 here. So tell me what's half of 32. Okay, so let's start with that and let's just see if that will work. And then, so I gotta remember what's here. I got an 18 here and a 16 here.
Oh wait, I think that might be.
Is that gonna do it?
And then you just have to put a 2 on the O2.
Not quite.
On the other side.
Well, actually, this is just a 2.
Well, I'm saying, wait, what am I
I've
saying?
got 18 times 2 and 16.
Oh.
That's a lot. It's a lot of oxygen. So I'm going to have to do, you're right, I have to do something to that O2, but I have to do something bigger than what you're thinking. All right, so let's count them up. I wish I had them up there individually, sorry. 18, right? 18 times 2. What's that? Plus 16,
36.
plus 16 more.
Well, 58. Yeah, that's fine.
So then I have
No,
16, which oh look, I have 16 there and 16 there. So really I gotta just deal with that. Oh, that makes it really easy. That makes it really easy. All right, because if I've got 16 here and I put a 16 there, what's the only other number I've got? In front of the CO2, what did we put up there? 18. I could just put an 18 right there, y'all look. There it is, boom. Yay, yay, even numbers. I love even numbers. All right, do you see how we got there? Now, if I had been sitting down with a piece of paper and writing everything down, I think I would have found that more easily. Yes? Instead of just trying to piece it out in your brain. Some of you can do that. Some of you have those brains. I don't have that brain. I got to use scratch paper. So think about scratch paper next week for our quiz. And look at that crazy, crazy equation right there. I will tell you some of the most difficult ones I've ever done have been combustion reactions because of these gigantic things you get over here at the end. Okay, let's try this one. Iron chloride plus sodium carboxide, or is that carboxide? It gives me whatever that thing is plus salt. Whatever Fe2C309 is, no idea. Are we balanced? No way. No. And we have a 3 and a 9, yikes. All right, let's start with our iron. That's going to be easy, right? Probably. Can we just put a 2 in front of our FeCl3? We could try it. That's a good place to start.
Yeah,
What does it do to our Cl?
makes it 6.
So what do we need to do to our sodium chloride?
Put a 6. So,
Yeah, that's right, to put a 6 there, which that messes this over here up. But look, I have a relationship between 2 and 6. What is that relationship?
3.
3, yeah. So I can use my odd number there. Let's bring it in. This is balanced. Let's just make sure we see how we got there. We definitely know how we got the 2 in front of the FeCl2, right? We know where we got that. And then we went over here to take our 6Cl3 and gave it 6 to our NaCl at the end. And now our sodium needs to be 6. So there's the magic. 3Na2 is equal to 6. Now is our C, the 3 works for our carbon as well, and our C3 over here. And let's see if our oxygen, 3 times 3 is 9. How about that? It all balances out in the end, because God is good. He's very orderly that way. So even with my 3s and 9s, I'm okay. All right, so start there with the easiest beginning. So the easiest beginning was putting that 2 in front of that iron. I may have to change it later if something else gets mixed up, right? It gets messed up by, I may have to make it a 4 or something like that. But just start there and see if you can get it there. All right, number 13. All right. Ammonium chloride plus barium hydroxide will give me barium chloride plus ammonia plus water. Now let's see if it's balanced.
Wait.
Keep in mind when I'm using, remember what this is called when they're together? A polyatomic ion, remember that? Hydroxide, that too is going to apply to both things in there, y'all. That subscript applies to both of those, okay? Whereas a subscript like here in the Cl2, that little 2 only applies to the Cl, right? But when I have parentheses like that, it applies to everything. All right, so we're not balanced. The easiest way to see I'm not balanced, I have only 1 chloride here, I have 2 on the product side. So there's the easiest way to see that I'm not balanced. So who wants to go for it and tell me what I'm doing? Let's go ahead and start with, okay, our bariums are balanced. I'm thinking let's start with our chloride. So if we put a 2 in front of NH4Cl, would that be a good start? Yes. Hooray. Does that balance everything? If I put a 2 there, all right.
But then it makes the hydrogen.
But our barium's okay, right? And our chloride's so this barium chloride is okay. But now I got to deal with these two over here, our ammonia and our water. So how can I fix those? Don't forget my OH is here. All right, no O's over here. So what we're going to do is actually add some 2's in. We're going to put a 2 on our NH3 and a 2 on our H2O. So once again, if you had your chart out, you can see how that would fix it and that would work. I can see y'all are really excited about balancing equations. Yeah. Okay. I think that's our last one. I'm going to show you though. Does everybody have that written down? I'm going to show you the one we did already, but it's going to do it for us so we can watch it all the way. Everybody's got this? Okay. Remember your homework tomorrow. Here it is. It's going to go by itself. I'll put a 4 there. 4 is 4. Makes that 16, makes that 12. Then our 6 there, and then finally right there is our 12. See how it's doing it by itself? So, before and after with each one of your elements on there, each one of your atoms on there, and you'll be able to figure it out. Okay? How do y'all feel? All right, now that's it. We're done. Hooray. So next week our quiz, bring your study guide and practice problems. Definitely practice those density problems and practice those balancing equation problems.